Hello everyone. Welcome to class 9 lecture on the nonlinear analysis of the course FA of Aerostructures. So far in this course, right from the introduction to aeronautics, we have seen the creation of the geometries within Patron and Nastron, and then also the creation of the material properties, loads and boundary conditions, etc. And then I have introduced you to the Nastron in class 7, and then in the class 8 we saw the post processing, various different options for the extraction of the results and the analysis of the post process post processing options. So now moving to class 9, I'm going to discuss with you the types of nonlinear analysis. And also, before going into the nonlinear analysis, it's very important to have a very clear understanding of what is the linear analysis and what is the difference between them. So I'll just quickly run through the slides before I get into the Patron demonstration. So the topics covered would be linear static and the nonlinear static analysis, and the types of input and outputs that is required to run the nonlinear analysis and the linear analysis using Nastron, and the things we should watch out. So before understanding the nonlinear analysis, it is very important for any engineer to have a very clear understanding of the linear concepts, how the structure behaves, and what is the influence of the stiffness on this both linear and non-linearity. So first of all, the what is stiffness? Stiffness is the it is the property of the material that it responds to the applied load in a certain fashion. So we can say that stiffness, it is the resistance to the applied loading. So the term stiffness defines the fundamental difference between the linear and nonlinear analysis. So stiffness is a property of the part or an assembly that characterizes its response to the applied loading. So the behavior of the structure depends on the stiffness of the structure to which the load is applied. So there are three primary factors that affect the stiffness. So what are those? Those are shape, material, and the support, the boundary conditions. So the shape of a part or an assembly, whether it is an I section or C section, in terms of beam or in terms of plate, then it is a thick plate, thin plate, etc. So and then the material, because the material involves a very huge, very big role in the driving the stiffness properties, because we have axial stiffness, it is EAE, and then the flexural stiffness is EI. That comes into picture the mainly the Young's modulus on the all the material properties. So the example of the material is like you can take steel and aluminum, where steel is 3 times stronger than an aluminum. So material, the type of material plays a very important role in driving the stiffness of the structure. And then the last one is the boundary conditions. So again, if it is an clamped boundary condition, fixed boundary condition, or an hinged boundary condition, the boundary condition plays a huge role in the behavior of the structure. So with regards to the fundamental FEA equation, where force is nothing but stiffness times the displacement. So the stiffness is nothing but force divided by the displacement. So here the FEA, within FEA there is a stiffness matrix where the stiffness matrix for the entire group of elements or the entire model is being computed. and then assembled, and then it is solved to find the unknown values. Unknown is the displacement. So the linear static analysis or the linear analysis is the stiffness matrix depends on the geometry, material properties, and restraints. And under the linear analysis, assumption is that the model stiffness never changes, and those equations are assembled and solved just once, which is the here the equation what I refer to is the stiffness matrix equations or the stiffness matrix in the finite element model, or the elemental stiffnesses and the nodal stiffnesses that is being assembled in a global stiffness matrix, which is solved once, and there is no need to update the stiffness matrix while the model is running. And most importantly, the in the linear analysis, the stresses are in the linear elastic region. Since the stiffness and the behavior of the structure doesn't change, so the whatever the loads, the internal loads of the structure, that is the stresses, stay within the linear elastic region and behaves the Hooke's law. So thus the linear analysis follows a straight path from the problem formulation to the computation. It is very straightforward method. So moving to the nonlinear analysis, you see the stiffness matrix which is coming from the elements should be keep on updating. It should get updated as when the nonlinear time step or the nonlinear solution is in progress. So why it is the case? The reason behind the there will be a change in the equilibrium of the structure. So the behavior of the structure, how it behaves, whether it's a large deformation or whether it's a plastic region, whether the material goes to from elastic to plastic, and those kind of reasons, the stiffness matrix needs to be updated, and it's an iterative process. The solution process is an iterative process, so the solver takes a bit of computation time to solve any nonlinear analysis or a nonlinear FE job. So it's an iterative process, and those iterations increase the amount of time that takes to obtain the results, that takes the time to solve the problem, and obviously obtaining the generating the results. So that is the fundamental difference between the linear and the non-linear analysis. So what types of non-linearity we have? We have primarily three types of non-linearity that is being addressed within the FEA community, which is geometric nonlinearity, material nonlinearity, and contact analysis. So first we'll see one by one. So geometrical nonlinearity. A geometric nonlinearity results from large displacements. Okay, it's when we say geometry, it is mainly the cross section. It is influenced by the dimensions of the structure and not by the material. So obviously the name indicates geometry and the name indicates material and the name indicates contact. That is, something is in contact or something is interfacing with something or some in a. So in this case, the first case, geometric nonlinearity, it will be the cross sectional area, the dimensions, whatever may be the geometrical variable that is driving the nonlinearity, that is causing the nonlinearity. So it might be the result would be a large rotation or the large deformation or a large translational displacement, etc. So a generally accepted thumb rule suggests that it is conducting a nonlinear geometric analysis. So whenever you say that the deformations are very large, if if it is very large in the sense, it might be 1 by 20th of the path's dimension or larger than the 1 by 20th of the path dimension, then you can say that it is very large, and then you should go for it is sometimes what happens if An engineer runs the linear analysis, the results may not be a satisfactory one. So, and the displacements might be very large. When he checks the displacement plot, it will be a very large displacement. Then obviously you should rerun the model for a nonlinear analysis just to identify how the structure behaves. Nonlinear geometric nonlinear analysis. So another important factor is to recognize that in cases of large deformation, the load direction can change as the model deforms. So you see here it is vertical, but over here it is almost parallel. So the direction of the load changes along with the structure. So one is the based on this point, the direction of the load changes. Most FEA commercial available tools, they offer few options while running the analysis, that is generating the following follower forces or none or not. What it means is like if the direction of the load changes depending on the part and assembly design of the part, so it will generate the follower forces. If not, then it is non-following load. So the next one would be the materials non-linearity. A material non-linearity is nothing but the loss of linearity in the stress strain relationship. What it means the material is no more elastic. It doesn't stay within the Hooke's law, and then that means it goes from elastic to plastic, or it might be elastic to brittle or something else. So that is not definitely elastic. So a linear material model assumes that the stress to be proportional to the strain. That means it assumes that the higher the load applied, the higher the stresses and deformation will be proportional to the changes in the load. It also assumes that no permanent deformations will result, and that once the load has been removed from the model, will always return to its original shape. Okay, so whereas the nonlinear model takes into account the plan, that is whatever so far we have discussed is the linear model, but whereas the nonlinear model takes into account the plasticity effects, which are large strains, and there will be a permanent deformation. And so if you are using a nonlinear material, if the component is made from both combination of metals which are linear mostly, and then the nonlinear metals or nonlinear elastomers, polymers. So in that case, it is advisable to run the nonlinear FEA run to generate the accurate stresses and accurate to get the accurate understand the accurate behavior of the structure. So typical cases are plasticity and then finite elasticity for hyperelastic materials like rubber and polymer. So there will be some people might be from an automotive background. So in for automotive cases, it's mostly nonlinear material because they use they use soft cushions, soft rubbers, soft sealing rubbers, and mostly it is nonlinear material nonlinearity comes into picture. So here in this slide, I have shown you some of the graphs that will be helpful for you to understand the nonlinear and the linear behavior. The very first top graph shows the simple linear elastic behavior. This is a simplified representation of the linear elastic behavior, and whereas the next one represents both the elastic region and the plastic region in a simplified fashion, and the point that changes from elastic to plastic is the yield point. And over here you can see the graph for various types of materials, that how they behave. Yeah, perfectly brittle material like a glass or a ceramic, which will have a typical linear elastic region at the end of the region in breaks. Once it reaches the yield point, it breaks instantaneously. And whereas the second one is the strong material which is not ductile. So maybe the steel or some of the cast irons which are really strong, but at the same time their behavior will be brittle. They will have a linear elastic region but little bit of plastic region, and then they will break. And the next comes the your ductile material, which is typical most metals, and then the typical aluminum alloys, which is widely used in the aerospace industry and both in the automotive industry, bodybuilding. So those behaves as a ductile material where you have the elastic region and the plastic region and the strain hardening, necking, and the failure. So and then the perfectly plastic material where it will have only strain for smaller amount of stress, only a large amount of strain is resulted. So this is a typical, the usual stress strain graph which shows the elastic region, which is the proportional limit. Once the proportional limit is crossed, it is still within the elastic region, but it is the behavior is little bit plastic. For any amount of stress, there is a little bit increase in the strain, and then it reaches the yield point, elastic yield point. And then finally what happens, which is the upper yield point, and then finally after this it is fully plastic. So it goes to the lower yield point, and then the strain hardening, where for any amount of increase in stress there is a large amount of strain that is resulted in the material. And then finally it reaches the ultimate stress, and then finally it necking, it goes through the, finally it fractures. So that is the concept behind this, how the material behaves. And this lower yield point will correspond to the permanent set. Permanent set is the permanent deformation. So over here you can see I have put a graph for low and medium carbon steels and then the aluminum alloys. So these are the stress strain graphs, obviously, that indicates the behavior of these carbon steels and the aluminum alloys. Carbon steels, low and medium carbon steels, are still the ductile material. They will indicate a clear upper yield point, lower yield point, the elongation, which is the strain hardening, and finally the necking and the fracture. Whereas the aluminum alloys, it will be a little bit different, where you have the the 0.1 percentage proof stress. Proof stress is nothing but the your yield stress, but it is with a permanent set. Permanent set for the permanent, it represents the stress that is above the proportional limit, but still elastic, but the behavior is plastic. It is still within the elastic region, but the behavior is little bit plastic. And then the first point, the 0.1 proof stress is called the upper yield point, and the 0.2 is considered as the lower yield point, which doesn't clearly exhibit, aluminum alloys doesn't clearly exhibit something like this, where the upper yield point and the lower yield point is clearly exhibited by the low and medium carbon steels, but whereas over here it doesn't exhibit anything. So the 0.2 percentage is proof stress would be the 0.1 percentage, and 0.2 would be the permanent set, that would be the permanent deformation. And then finally it continues where the elongation, strain hardening, and it reaches the ultimate stress, and then finally necking. So this is a typical behavior of the aluminum alloy and aluminum alloy steels. And over here I have put the perfect nonlinear behavior, and over here you can see I have put a graph of some materials such as cast iron and concrete, which doesn't clearly exhibit any linear regions, and the plastic regions. It's very difficult to make out from this. It's just a curve in which you can see that even the linear elastic region, it's not a perfect straight line. So that means that it doesn't exhibit any linear elastic region. So in for these types of materials, which the entire straight strain curve itself is something like a nonlinear curve, it's very complicated. So for these cases in the engineering community, we use, even within the Patron and Nastron, instead of Young's modulus, we use the tangent modulus or the secant modulus for the regions, which is trying, we can try to idealize or assume it that something falls within the elastic, that is something below the, something closer to its proportional limit of the material. We can consider it as a straight line, and then we can calculate the tangent, sorry, we can calculate the secant modulus, and then feed this secant modulus into the Young's modulus tab in the FE tool. And similarly for the plastic regions, the tangent modulus will be calculated, and they will draw a straight line which is passing through the sum of the points of the plastic region curve, and then they calculate the tangent modulus, and that will be fed into the Young's modulus. So in this way, the curve for these kind of materials can be idealized, can be assumed, and we can brought we can bring it down to fit into the realistic, somewhere around realistic, you know, elastic and plastic regions for the ease of the analysis. And over here you can see that a normal stress strain curve, which is something similar to the aluminum alloy, where it exhibits the linear and the nonlinear regions. And when the when it reaches the 0.2 percentage proof stress, and when it unloads, it comes down and it sits as a permanent set of the plastic strain. But the whole, this region, this is the whole region is under elastic, still under the elastic stress, but the behavior might be non-linear above the proportional limit. Once it crosses the proportional limit, the behavior changes to the non-linear elastic, finally until it reaches the yield point. After that, it is fully non-linear. So the entire region is the elastic region from the permanent set. So the total strain would be the strain caused by the permanent set, which is plastic, and the elastic. So this is just for the understanding how the linear and the non-linear scenarios or the linear behavior of the materials vary. So now we moving forward, I'm going to discuss with you, take you through the steps involved in the linear and non-linear analysis within the FE analysis, and then I will also going to discuss further on the important considerations and important commands and important parameters that we need to specify for the nonlinear analysis and the linear runs.